Okay, I think we'll get started. So big day today. We're talking about Newton's laws. Last time we talked about forces based on potential energy. So we saw that the definition of force, one definition of force was the gradient, spatial gradient of the potential energy. Well, forces can play a fundamental role in how objects move, and it'll be our critical connection between the motion, the dynamical motion of objects, and the cause of that motion. So one way to talk about how objects move, or the dynamics of objects, is through what's called Newtonian mechanics, and that's with force as the central player. And that's what we'll do for this early series in physical chemistry. As we go further up, we will see that it's a little bit more general and broad to talk about motion based on the energy itself, and that's different formulations of mechanics called Lagrangian mechanics and Hamiltonian mechanics. But a good place to start, and a good place to start for us, is with Newtonian mechanics grounded in force. The reason for that is forces cause changes in motion, and this brings up Newton's first law, which says that in the absence of a net force, so we can have different sources of forces, and what we need is a net overall force. An object, so if we don't have that, an object that's at rest will remain at rest. Also, an object that's undergoing uniform motion. So uniform motion was, if you remember, the case where we have constant velocity and there's an absence of force, then that object will continue to move along a straight line at that same velocity. All right, well, we'll refine this notion, and we need a few ideas, and then we will add some additional laws, and together they can form the basis for understanding how objects move and calculating how objects move. All right, so let's characterize these forces. Now, forces can either be a pushing force, so I could, if this is a ball or this pen maybe, I could push on this pen, okay? Or a pulling force, so I could attach a string here and pull on that. Then a force mediated by a string is called a tension. Right? That's a tension force that would pull this along. This push and pull is done by something called the agent. So in this case, if I'm pushing here, my finger is the agent. Here, if I'm pulling, well, if it's attached to a rope, then the rope is the agent that's pulling this along. Or you could say the rope and me, this whole other object, or other agent is the rope and me, but the object is the pen, the agent is what's pulling. Acts on these objects. Okay, well, there seems to be a big asymmetry here between an object and an agent, and that's only for convenience. So we will see as we progress through the rest of the lecture here that this is a bit artificial, and it's only a way to frame how we're thinking to help organize our calculations, isolate on the thing that we're interested in. So in a typical situation, there's going to be one thing that's the obvious object. So an ion, a molecule, or this pen, and then something else acting on that object to cause that object to do something. And it's very natural to think of that as the agent. But that is an arbitrary labeling, as we will see. Now, these forces can be either what are called contact forces. So I'm contacting, the agent is contacting the object to cause the motion. Or they can be long-range forces. So imagine this was statically charged. Maybe, let's say, it had an overall positive charge. And let's say this was if I had an overall negative charge, then I would have a pulling force, but I wouldn't be in contact. Or if this was positive and this was positive, I'd have a pushing force, but not in contact. So a lot of the forces we're going to be interested in physical chemistry as we progress through these courses are long-range forces due to ions and charges of molecules. But, of course, we will be interested in contact forces as well. Now, as we learned last time, force is a vector quantity, And so we have to add them vectorially. So if we have a force in one direction, a force in another direction, and they add together, they're both acting on an object. So this object is, maybe I'm pushing this way and pushing this way, then the net force is up in this direction. All right, well, one natural way to decompose the forces as related to the object is to talk about normal and tangent components. Now this is just, the force can come in at any angle here, but we talk about a normal component to a surface as being, if this is my surface, then 90 degrees to that. If you imagine a point on that surface and then draw, so a point here, if I'm this way, I draw a line here, I go 90 degrees to that line, I draw a tangent line, 90 degrees to that line. That's called a normal direction. So this would be a normal force. The second component is the tangent force, so force along the tangent. So this is my object. Here's my normal force. Here's my tangent force over here. Over here, here's my normal force. Here's my tangent force direction here. All right. Well, let's refine this notion here. Forces causes change in motion. Forces actually cause acceleration. And that's the basis for Newton's second law, which says that an object with mass m will undergo an acceleration when subject to a net force. And mass is important here because force is proportional, or the acceleration is proportional to the force, and that constant of proportionality is mass. So given the same force, a larger mass will experience less acceleration than a smaller mass. So this formula is the central starting formula for the Newtonian mechanics. So understanding mechanics based on forces. F equals ma. From this equation, we can quickly get units here. So the SI unit of force is something called the Newton. And it is a compound unit. And we can see that compound right away. Mass, base unit of kilograms. Acceleration, the base units are going to be meters per second squared. So kilogram meter per second squared is the SI units for force. Okay, so this idea of net force is important, and there's a nice bookkeeping way to do this, to keep track of all this, and that is to take whatever physical picture that you're working with and create something called a free body diagram. Now I'm going to go through just this very quickly, and I really encourage you to go to the textbook that you're working with. Any physics book that you have will have a nice section on the steps to draw free body diagrams, and I'd encourage you to master this because as I like to tell my students, you can never go wrong by drawing a free body diagram. Like maybe you could have done it without it, but you can't go wrong by doing it. But you can go wrong sometimes by not drawing a free body diagram. All right, so in a free body diagram, we identify the object. So let's say we're interested in this ion, and we've got this long, massive, extended electrode here. If this ion is close to this will experience a uniform force, and therefore, a uniform force, and it will be in this direction because this is negative and positive. So there's going to be a net downward force here, electrostatic. Well, this has a very simple free body diagram because there's nothing else around. We're ignoring gravity here. Let's just ignore gravity. And we would draw then a solid circle to represent the object, and then we will draw all the forces acting on that object, which is just this electrostatic force. And so we know that this will accelerate in the direction of the net force. See, if we go back to this equation, mass is a scalar, so the acceleration has to be in the same direction as the force. So this will accelerate straight towards the electrode. Well, now let's look at a situation where this has reached the electrode, and it's just sitting there at the surface. It's not penetrating into the electrode. And so this surface is providing some kind of counterforce to stop that acceleration. So it's easy to think, oh, there's no forces here. Well, there are forces, and the free body diagram will expose that. And we still have the electrostatic force, but this surface is providing a normal force that is holding it in place. Okay? And how do we know how big that normal force is? Well, this is sitting still. So we go back to the first law. This is at rest, so there must be no net force. And that's the thing about these normal forces. You have to look for them, and they're not set. So we will learn later how to calculate how big this force is based on what this charge is and what this charge is. But the normal force will simply act and be as large as it needs to in order to maintain a zero net force. So if we were to reduce the charge here, reduce the charge here, this would shrink. The normal force would not remain the same, because if it did, we would see an acceleration upward. So instead, the normal force will adjust to hold the total force, or the net force, to zero, so that we have no net acceleration. Let's look at a little different geometry here, just to help nail down this normal force idea. So let's say there's some kind of obstruction here that's at this angle. There's no charge here. The charges are down here. Well, let's draw the free body diagram for this. So this dot again represents this ion. It is experiencing this force straight downward. This ramp here, or obstruction, can only provide a normal force. So that normal force is in this direction. Maybe a little too long here. Perpendicular to its surface. And thus, when we look at our free body diagram, and we vectorially add these component forces, so this, then we have a net force in this direction. And very natural, I think we can all see that what's this ion going to do? It's going to slide down this ramp. So it will accelerate down that obstruction until it reaches the electrode. And we can see that here from the free body diagram. All right, well, we haven't done too many of these, so if you feel good about it, good. But if you feel like you need a little more work, I think it's really valuable time spent. Again, any physics book will have a really good discussion of this. Just as one quick aside, in the notes, I use gravity and rather than these electrostatic cases. And just as kind of a quick aside, gravity, which we won't talk as much about in this course because we're focused on building up our curriculum for physical chemistry. But certainly in general physics, the case of gravity is really important. And we even call this a free fall problem. It's of the free fall type. And that's really coming from a gravity situation. But notice this is exactly the same as, in terms of mathematical form, as a mass being attracted, a small mass being attracted to the Earth, right near the surface of the Earth. So if we're at top of a building and we drop a ball, that would be the similar forces, the functional form of these forces involved. One due to gravity, one due to electrostatics. So the same free body diagrams would work in those cases. All right, well, let me come back to this artificial asymmetry here. Now, when we look at cases like this or cases like this, we say, okay, we're interested in the ion. This electrode has to be there for this to be working, but we're saying this is just, it's just there. It's acting as the agent here. But in reality, what if we were really interested in electrodes and we didn't care so much about the ion? Then we would be wondering, what is the ion doing to the electrode? And in the case of a really small ion in this big macroscale electrode, basically nothing, but not completely nothing. So almost nothing, but not exactly nothing. In very much the same way that this pen is attracting the Earth towards it just as much as the Earth is attracting the pen towards the Earth. So if I drop this, well, the Earth is attracting the pen, but the pen is pulling the Earth up, right? Well, of course, the Earth is so much more massive that essentially nothing happens. But we could be talking about the Earth as the object and this as the agent. Right? So this is an artificial thing. So it's really two objects. They're interacting, and so we can draw two free body diagrams. We can draw one for the ion, and here we will have a normal force upward. I'm going to actually put these in two different colors. Try to find a green here. An electrostatic force downward. Well, let's look at the electrode here. Draw its free body diagram. Well, now the electrostatic force is upward. And the normal force is normal to this ion. So draw the ion. Here's the normal direction, right at the point of contact. So at the point of contact, the normal direction is downward. So notice I've got a pair here and a pair here. These are called action-interaction pairs. So the action-interaction pair is the normal force pair here and the electrostatic force pair here. And every situation like this, for every force on a free body diagram, there's a partner or pairing force on a different free body diagram. So that's important. You should never be identifying action-interaction pairs on the same free body diagram. This is another example of how the free body diagrams can be helpful instead of just looking at the picture itself. So we're trying to identify what are the pairs. Well, the normal force here is a contact force acting up on the ion. The normal force from the ion is acting down on the electrode. That's the pair. The electrostatic attraction is acting upward on the electrode and downward on the ion. Okay? So it takes a little while to practice this a bit, but you can have some hard, fast rules for yourself. You should never find the pair on the same free body diagram. And then here will come Newton's third law. One force you find here, you should find an equal but oppositely pointed force over here. So the action-interaction pair will be of the same magnitude but pointing in opposite directions. And so that is the third law. Every force occurs as one member of an action-reaction pair or an action-interaction pair. So you'll often hear in sort of layman's terms the third law as For every force, there's an equal and opposite. For every action, there's an equal and opposite reaction. That's what this is meaning here. All right. So that kind of gets us through the laws, but let's look at a few ancillary pieces of information that we're going to need here. The first is the idea of mechanical equilibrium. So first of all, we're definitely going to be spending some time with chemical equilibrium. Now that will be the basis of Introduction to Physical Chemistry 2. Won't see a lot of it in Introductory Physical Chemistry 1, but we will be seeing mechanical equilibrium throughout all 3 of the courses. Now mechanical equilibrium, here we're talking usually about a couple of objects or one object and some agents, that sort of thing. Whereas chemical equilibrium, we're talking about a chemical reaction that's occurring in a beaker. Mechanical equilibrium, we'll dispense with chemical equilibrium now. So chemical equilibrium is we've got this reaction happening in the beaker. We pour 2 things in, we see something happen, and then it comes to a final state. We call that a chemical equilibrium. So as we look at the beaker, we don't see any change. But behind the scenes, at the molecular level, reactions are happening all the time. Products are being turned back into reactants, and reactants are being turned into products, but just at an equal rate. And so the net result is an equilibrium. Yet it's very dynamic what's happening in the beaker, and any given one molecule is not in mechanical equilibrium. Okay, so let's focus here now on mechanical equilibrium. So now we're just going to be thinking about single objects here. Now we have two basic types here, stable and unstable equilibrium. Let's imagine this sort of egg-shaped object or blob, asymmetric blob object here. And we can envision this would sit very nicely on a table like this. And if I were to make a little disturbance, like a little what's called a perturbation. So if this is sitting like this, here's our blob object. I make a little perturbation this way. Well, it will come back to this equilibrium position. So if it returns to its equilibrium position upon a small perturbation, we say that's stable. Now let's turn it upside down, try to balance it on the tip here. And it certainly can balance there indefinitely. So it's at equilibrium, it's not moving. But if I give it a little perturbation here now, a little perturbation, then whoop, it'll tip over. It will leave that state. And so that's what we call an unstable mechanical equilibrium. Now, just something that might be not super clear, we aren't necessarily looking for completely at rest as we're looking at it. So let's look at these 2 carts. One is sitting still. One is moving at a constant velocity. At a constant velocity. These are both under stable mechanical equilibrium. If I poke this cart a little bit, it will not deviate from its state. If I poke this cart a little, it will not deviate from its current state. So taken together, let's connect back here with the first law. What does it mean to be in equilibrium? Well, there's no net force. Now, of course, there are forces here. The free body diagram for both of these guys would be gravity, call that a weight force, and a normal force. So there are forces present, but they're balanced. So there's no net force, and so the object here will remain at rest. Same with the cart. No net force. In fact, the free body diagram for the cart is the same here, a weight force and a normal force. But now let's do the free body diagram for this one. Might be different. Well, let's see. Oops. No, it's not different. So it's exactly the same as if it were at rest. And so there's no net force there. No net force. Let's go on to the second law. Well, what does that mean? That means these things will not be accelerating. Will not be accelerating. All right, well, let's pick up one final thing, and we'll come back to this at various points in the course. But let's pick up this idea of reference frames. Notice there's a little bit of awkwardness to the statement of the first law. We have to have two parts to it. If the object is at rest, it will remain so. If it's in motion, in uniform motion, constant velocity motion, it will remain so. Okay. Well, maybe it seems a little unsatisfying that there's such a fundamental law of nature and we have these two cases. Well, there really aren't two cases. It's really just one case. And I think we can see this best by looking at this example here. So let's imagine these three people, and two of them are on this train bed moving at speed u in this direction, or velocity u, so this speed in this direction. And then we have one person on the ground. The person here will start running on the train bed. This person will remain still. On the train bed, this person will run at a velocity v. So what the reference frame is what is the point of view in which you're viewing the physics, or the physics is being viewed. So there are three natural reference frames here. Of course, there's infinite number of reference frames, but there's three natural ones here. Let's first look at the reference frame in which this person is standing still. This person would see this person moving in this direction at speed u, right? Because the train is going this way. So this person viewing this person would see this person moving at speed u. This person would see this person moving at speed u plus v. U plus v, moving in this direction. And so let's say the train's moving at 5 meters per second, person's running at 3 meters per second. In the reference frame of this person would be moving at a constant velocity of 8 meters per second. Now this person would report that differently. This person would report this person running at 3 meters per second. Right? So this person would see this not at u plus v, but simply v. And they would see this person going at minus u, because from the point of view of this person is moving this way. So if this was considered the reference frame, this object would be moving this way, this object would be moving that way. And finally, the last sort of natural reference frame here would be this person. Well, they would see this person coming at them at minus v, because from this frame, it looks like this person is moving this way. And then this person would see, if this person looked at this person, they would be moving off in this direction at a minus u minus v, or a minus u plus v. And so what you call the reference frame determines what's at rest and what's not at rest. These are called inertial frames. And so, yes, here it looks like these two things are different. But if we were running alongside this at this speed, then this would be standing still. So effectively, there's always a frame in which the object that's undergoing uniform motion is at rest. So there really is no difference between being at rest and being in uniform motion. They just differ by what frame of reference the observer is observing them in. All right, so that then sort of clears up this a little bit unsatisfying nature of these two statements. So we could say, in the appropriate reference frame, an object that is, in the absence of force, an object at rest will remain at rest. Because we can always find an inertial frame in which that object is at rest. Again, an inertial frame is one that, if you have two inertial frames, they're moving at a relative constant velocity from one another. There's no acceleration or rotation in those frames. All right, so this is the crux of sort of general physics, Newton's laws, Newton's Newtonian mechanics, and we went through it fairly quickly here and without a lot of examples. So I would encourage you here now to take a little break from going on to the next lecture and get into your whichever physics book you have. We'll have tons of problems on the first, second, and third law, and I would really get that solidified before moving forward. So do the homework from the notes, and then try to do extra problems and do a little extra reading of these particular sections in your physics books, because this is critically important framework, like foundational groundwork for you to have a good understanding of. All right.